252 million years ago, the sky over Siberia turned black. Not for a day, not for a week, for thousands of years. The ground itself was on fire, not burning forests. Burning coal seams buried deep underground, ignited and unstoppable. Above them, cracks in the Earth's crust split open for over 1 million square miles. Molten rock poured out in sheets. This wasn't a volcano. This was almost the entire planet, exhaling fire. And when it was finally over, more than 90% of all life on Earth was gone. Not 90% of one species, 90% of everything. Every reptile you've never heard of. Every strange, sail-backed predator. Every insect the size of your hand. Gone almost all at once in the worst single event life on this planet has ever survived. Scientists call it the Permian Triassic Extinction. Most people just call it the Great Dying, and it very nearly wasn't survivable at all. To understand how close life came to ending, you have to go back further. Back to a world before the Great Dying. A world that, on the surface, looked stable, even thriving. The Permian Period began around 299 million years ago. This was Earth long before the dinosaurs. The land was dominated by creatures that looked like they belonged in a fever dream. Dimetrodon, a reptile-like predator with a massive sail of skin running down its spine, used to regulate its body temperature in a world without fur or feathers. Gorgonopsids, saber-toothed hunters distantly related to the ancestors of mammals, stalking prey across supercontinents. Insects, the size of dinner plates, drifted through oxygen-rich air. All of this life existed on a single landmass, Pangaea. Every continent on Earth fused into one enormous supercontinent, surrounded by a single global ocean called Panthalassa. And this mattered more than most people realize. A single continent means a single climate system. Deserts stretching for thousands of miles. Interior regions cut off from ocean moisture. Life on Pangaea had already adapted to extremes most modern ecosystems never face. But even Pangaea's ecosystems had never faced anything like what was coming. In what is now Siberia, magma began pushing up from deep within the Earth's mantle. Not through a single volcanic cone, the way most people picture a volcano. This was different. The magma found a weak point in the crust and simply broke it open, across a region larger than the entire United States. Geologists call the result the Siberian traps. And traps, in this case, isn't a metaphor. It's the layered, stair-step rock formations that lava leaves behind when it erupts not once, but again and again, for hundreds of thousands of years. Here's the part that made it catastrophic. The magma didn't just erupt onto open ground. It pushed directly through massive underground deposits of coal, oil, and salt. As it burned through them, it didn't just release heat. It released almost unimaginable volumes of carbon dioxide and methane straight into the atmosphere. Think about what that actually means. This wasn't simply lava reshaping a landscape. It was the Earth burning its own fossil fuel reserves all at once over a geological instant. Dr. Seth Burgess, a geologist who has spent years dating the Siberian traps with extraordinary precision, helped pin down just how fast this eruption sequence unfolded. And fast, in geological terms, is still almost impossible to picture. The main pulse of eruptions appears to have occurred over roughly 300,000 years. That sounds long. In the history of a 4.5 billion-year-old planet, it's barely a blink. And within that blink, the chemistry of the entire atmosphere and ocean shifted beyond anything life had adapted to survive. Carbon dioxide levels didn't just rise, they spiked to levels many times higher than anything in the several 100 million years before it. Global temperatures climbed by some estimates more than 10 degrees Celsius, Ocean temperatures at the surface may have exceeded 40 degrees Celsius in places, warm enough that in some regions, complex marine life simply cannot survive. And heat wasn't even the deadliest part. As carbon dioxide dissolved into the oceans, it triggered a second crisis: ocean acidification. The chemistry of seawater itself began to change, making it harder and harder for marine organisms to build shells and skeletons out of calcium carbonate. Reef-building organisms, some of the foundation species of entire ocean ecosystems, began collapsing. At the same time, warmer oceans hold less oxygen. Vast stretches of ocean became what scientists call anoxic, essentially dead zones with barely enough oxygen to support life at all. Paleontologist Dr. Jonathan Payne, who has studied the marine side of this extinction extensively, has pointed to this lethal combination as one of the reasons the die-off was so severe in the oceans specifically. Heat stress, acidification, suffocation, all three compounding each other at the same time. On land, the story was just as brutal. Wildfires swept across Pangaea's interior. Vegetation that had anchored soil for millions of years died back, and without root systems to hold the ground together, massive erosion events followed. Rivers changed course. Ecosystems that had taken tens of millions of years to develop unraveled in what was, geologically speaking, no time at all. Here's a question worth sitting with for a moment. If 90% of species died, what determined which 10% survived? It wasn't size, it wasn't strength. In fact, many of the largest, most dominant predators of the Permian world, the same sail-backed and saber-toothed giants that had ruled for tens of millions of years, vanished completely. What seemed to matter more was flexibility. Species that could tolerate a wide range of temperatures. Species that didn't depend on a single, narrow food source. Species that could burrow or otherwise shelter from the worst of the heat and toxicity at the surface. One of the most important survivors was a small, unassuming group of animals called the Dicynodonts, and specifically a genus known as Lystrosaurus. Picture something like a stocky, barrel-chested, pig-sized creature with a turtle-like beak instead of teeth. Not fast, not fierce, not, by any obvious measure, impressive. And yet, in the aftermath of the extinction, Lystrosaurus became one of the most successful animals on the entire planet. Fossils of it have been found on nearly every continent that made up Pangaea. In a world where almost everything else had died, this unremarkable, burrowing, tough little animal thrived. That's not a coincidence. That's a pattern that shows up again and again across Earth's history. Mass extinctions don't reward the most dominant species of the previous era. They reward whatever happens to be equipped for the specific crisis that's unfolding. And the qualities that make a species dominant in stable times are often the exact opposite of what it takes to survive a sudden, radical shift. It took an extraordinarily long time for life to recover. Some research suggests that complex, diverse ecosystems didn't fully re-establish themselves for as long as 10 million years after the extinction. 10 million years of a comparatively empty, unstable world, before biodiversity climbed back toward anything resembling its former richness. But recovery did come, and when it did, the world looked completely different. With the old dominant lineages gone, entirely new groups had room to diversify. Ancestors of the dinosaurs. Ancestors of modern mammals. The Permian extinction didn't just end an era, it cleared the stage for the next one. Dr. Michael Benton, a paleontologist who has extensively studied the Great Dying, has described it as the closest life on Earth has ever come to a complete reset. Not the asteroid that ended the dinosaurs 66 million years ago. Not any of the other 4 major extinctions in Earth's history. This one. The Great Dying. The closest call complex life has ever had. So why does any of this matter now? Because the mechanism that nearly ended life on Earth 252 million years ago wasn't an asteroid. It wasn't a random cosmic event beyond anyone's control. It was massive volumes of carbon dioxide and methane entering the atmosphere faster than ecosystems could adapt. Rising temperatures, acidifying oceans, shrinking oxygen. A chain reaction once set in motion that proved almost impossible to stop. The scale of the Permian event was staggeringly larger than anything happening today. But the underlying chemistry, the relationship between carbon in the atmosphere, and the stability of life on Earth is exactly the same chemistry scientists study when they look at climate change now. 252 million years ago, the sky over Siberia turned black, and the world nearly ended. Today, the sky is still blue. And maybe that's exactly why this story is worth remembering. Thanks for watching. If you enjoyed this journey through the Great Dying, remember to like this video, drop a comment, subscribe, and click the bell to be notified the moment our next video goes live. All about the Triassic period and the strange new world that rose from the ashes of the Permian. And if you haven't already, check out our last video all about the Carboniferous period and the age of giant bugs right here on this channel.